Okay, next, let's see the second example. This is the synthesis of ammonia, which is a crucial chemical in agriculture industry, where we use this ammonia to make our fertilizer. So we have enough supply for our food when the tree have a good nutrient or enough sufficient nutrient. So what happened here is, what happened here is, according to our chemical reaction, one more hydrogen gas will react with 3 mole of hydrogen gas, and it will produce 2 mole of ammonia. So according to our chemical reaction, we can state that this is the change that we will have. This one will be reduced, nitrogen will be reduced, this one will be reduced, and then this amount of ammonia will be increased. So that's why we'll have this delta. That's why we mean by this one. So our delta N for nitrogen will be reduced by 1 mole. And then our hydrogen gas will be reduced with 3 mole. That's meant by this one. And it will be increased with 2 mole of ammonia. So each change of this one will be contribute to the change in the total gives energy of a mixture in a reaction. So if I can put it in a simple word, for example, if we have 6 mole, if we have nitrogen plus hydrogen, if we have like this, now if we have 10 mole each, however, when we do a reaction, this one at the early stage, initial, what happened here is 10 will be minus by 1 because 1 mole will be reduced, and then this 10 will be reduced by 3, and we have increase of 2. So at the final, we have a 9, 7, and 2. Why this 10 to 9? Why this 10 equal to 7? Why from 0 to 2? Because of this change of each of a species when a chemical or when a reaction occur. So there will be change in the species at the early stage of the reaction and also final stage of the reaction because of this one, because there will be a net change. So to find the Gibbs energy, so we can have, as usual, delta G equal to delta G of product minus reactant. So here we have one product and 2 reactant species here. Our product will be ammonia, and our reactant will be nitrogen gas and also hydrogen gas. So we can convert it to this one, chemical potential. So here we have a chemical potential of ammonia times with 2. Here is 2 delta N minus delta G of our reactant, mu N2 or chemical potential of nitrogen gas times with delta N plus chemical potential of hydrogen gas times with 3 delta N. So if we expand everything here, so we will get to delta N chemical potential of ammonia minus chemical delta N chemical potential of hydrogen minus 3 delta N chemical potential of hydrogen, and we can factor it. We can factor this each N here. So we will have we will simplify and we will have this equation. So in bracket we will have 2 mu NH3 ammonia minus mu N2 nitrogen gas minus 3 mu hydrogen delta N, and so we can move this delta N to our left hand side. So that's why we'll have delta Lg equal to delta G over delta N equal to equal to 2 mu NH3 minus mu N2 plus 3 mu H2. So here is our product minus here is our So this, from our equation, we can state that the chemical potential or mu depends on the composition of the mixture. Here is the amount, which will depend on the composition of the mixture, and then high if concentration of open pressure will be high. So our delta Rg will be high. It depends on the concentration of our species, and for our delta given energy will be changed as our composition of a reactant or product change. So here, if we plot the graph, it will be like this, and here is pure reactant and pure product. So we will have this kind of graph. So if we find the slope of each of a point, let's say A, B, C, point A, point B, and point C. Here, if we find the slope for this one, we'll get the delta Rg will be less than 0. So once where if delta Rg less than 0, we can say that this reaction is tend to form a more product, because this reaction is spontaneous. So this reaction is spontaneous to the product. When it's delta G more than 0, the product, this reaction will tend to decompose into reactant, while at equilibrium, the reaction has no tendency to form either reactant or product. So we can get this value of each of delta Rg either less, more, or equal to 0 according to the slope of this graph. Again, to find the slope of the graph, we have we need to find the slope, and then given by this equation. So from this equation we will get the value of our slope, and then we can determine we can get the value of delta Rg, and later on we can determine either it is more, less, or equal to 0. And let's see the variation of delta Rg with the composition. So here we will have a slightly a different formula, or different how to derive the delta Rg. However, still it uses the same concept, where the concept is delta Rg less than 0. If we got delta Rg less than 0, so we can say that this is spontaneous. So we can recall back at our previous lecture, where we can say that delta Rg equal to, we can write like this. So chemical potential of J, or J species, equal to delta J naught plus RT ln activity of J. So if we consider this equation where we have a reactant and also a product, so for delta Rg equal to delta G product minus delta G reactant. So product and reactants, each one, this one is our composition. So to have this one, we can say that delta Rg equal to, from here we have C mu C plus D mu D minus A mu A plus B mu B, here where this C is the coefficient of each this one, A, B, C, and D, and mu C is the chemical potential of each species in our reaction. And then to find delta Rg, what we do is we will put this equation to this one. So what we need to do is just replace the J species. So here is our species is A, B, C, and D. So we expand it. That's why we will get kind of this. It's a long equation. So you need to carefully derive from this one. This substitute is J with our species. So here how I simplify it. So from here we try to simplify it. So we will have this one, this delta Lj equal to C mu naught C plus D mu naught D minus A mu naught A plus B mu naught B plus RT C ln AC plus D ln AD minus A ln AA plus B ln AB. So here is, we simplify it. So next, what we need to do is, so we have this before. We already have this, so we also can change a little bit or modify a little bit of this equation by introducing the not factor here. So that's why it will be like this. So introduce a little bit not factor here. So and then okay, still remember this one. Okay, so what we did is we replace it with simplify it. We simplify it, become delta Lj naught. So here we have delta Lj equal to delta Lj naught plus RT C ln AC plus D ln AD minus A ln AA minus B ln AB. So here by using this relation, here is relation of ln. So we can simplify it. So it will be delta Lj equal to Lj naught plus RT ln AC power of C, AD power of D over AA power of A and AB power of B. So we simplify from here by using the ln rule. So here we can say that reaction quotient, so we replace it with Q, and then our final equation will be delta Lj equal to delta Lj naught plus RT ln Q. So here is how we obtain this equation from our chemical equation. So this is how we obtain it. So I hope that you understand how to derive it. I didn't expect you to derive it one by one, but I need to show it in order for you to understand how we get this kind of chemical equation, because it is very important for you if you want to derive or if you do a chemical reaction and you want to see activity of any species of chemical reaction in the system. So we can see that this here is our at equilibrium. So we have this kind of this is our equation. So at equilibrium delta Lj will be 0 because no change in the composition. Okay, you need to know this relation, delta Lj is equal to 0, and then from there you can put in here, you can replace here delta Lj less than 0. So 0 equal to delta Lj naught plus RT ln Q, and then we move this to our left hand side. We have delta Lj naught equal to minus RT ln K, and then we make ln as a factor. We make K as a factor. So that's why we will have K equal to exponential factor in bracket minus delta Lj naught plus RT.